This is Francisco Palacios. I'm gonna host with Tom Economou this meeting. Today is a very special meeting because it's our first meeting that we are broadcasting on YouTube. So we have prepared something special for today.
Yeah, so we realized that last week static, it wasn't as interactive, and we want to get people involved a little more. So we're going to try something new this week. The idea is we're going to take some questions from the forum. We're as a group going to discuss them and answer things that you guys are interested in, and we really want to get you guys to hear what you guys are working on in the code and what questions you have. So the idea will post things on the forum, and we'll go in and grab them and pull topics today that will kind of lead a discussion on.
And as today's meeting, we thought that it was a good idea to present the team at Stanford. So I will introduce myself. I'm working on optimal shape design, in particular in a joints method, and currently I'm implemented in the Invisit solver the adjoint capability. I'm also working in the scalability of SU2. Currently we are running in more than 2,000 cores. I'm be able to run SU2 in tens of thousands of cores.
So again, my name's Tom Economou. I am wrapping up a PhD here at Stanford. In the solver, I'm working on the unsteady features, so dynamic adjoints for unsteady flow problems. I have my hand in a few other things. Probably shouldn't admit it publicly, but if you're having problems with NS reader, you can send me an email. That's probably my fault. But yeah, so I'll pass it on. Santiago?
Hi, my name is Santiago. I've worked on SU2 and on steady flows. I've done some development of a gust model, aeroelastic, and I've used this for simulating vertical axis wind turbines and flutter boundaries.
I'm Heather, and working on optimization of hypersonic air breathing engines, and I'm getting started working with adjoints as well.
I'm Brendan Tracy. I work with SU2, mostly doing research on sort of new turbulence model development. I've also done some of the config parsing script, and additionally I've been working on sort of cool and fun ways to call SU2 programmatically.
My name's Andrew Wendorf. I've been using SU2 to get stability derivatives of aircraft, and am working on trying to get control surfaces that are implemented into meshes.
You want to say hi, our control man?
Off camera. My name is Aniket Aranike. I've been working on wind turbines, particularly shrouded wind turbines. I've been working quite a bit with the transition model in SU2.
Yeah, and this is like half of the SU2 team at Stanford. So we are everybody working in a different piece of the code, and we are really looking for contribution all around the world.
Yeah, and just to add, we already have contributions from a number of people have submitted pull requests and other modifications.
Yeah. In fact, we are modifying our web page in order to give the credit that they deserve to all these developers around the world. So I think we can continue with our meeting directly to the question that we have found in the CFD forum. So maybe you can speak a little bit. Sure.
So just to reiterate again, the idea here is we're going to go forum questions that we think are pressing, things that are really interesting for the larger group, and try to highlight and show some things that we think will be really useful for people out there, developers and users. So a few of these questions and kind of kick them off to you guys, but hopefully we can just have a little bit of discussion. And we're also going to try something new with a laptop here. We're going to pull some things over and try to do a screencast and show you guys stuff. So bear with us a little bit on that, but I think it will be useful. So first question, this is from John. They're looking to simulate supersonic aircraft with SU2, but it appears there are some non-physical points. So they want to know if this result is credible. So what do you think, Francisco?
Well, supersonic is one of the specialities of SU2. We have thought in supersonic, in particular in minimizing the sonic boom. So as you know, in the supersonic, one critical step is the choosing the right combination. As far as I have seen in this question, you are also using AUS. So the first thing that I would like to remember is that SUSM is a scheme that we have implemented only the convective part, not the Jacobian. So basically, when you implement a numerical scheme, you have the flux part, so where you compute the weight in order to compute the term, but also as we are running implicit simulation, we're required to implement the Jacobian. Currently, we are using the Jacobian that came from the row solver. My recommendation is first, if you have a wall, please try to implement the Jacobian for the USM. And we will appreciate a lot if you can do that. With the non-physical term, the non-physical point, you must be careful because that means that at a certain point in the mesh, you have some kind of negative density. You really need to take a look at that. So I'm gonna go to the software and I will show you exactly where this implementation is.
Say something?
You will see that we have the fluxes, the implementation of the fluxes. At the end of the implementation of the fluxes is where you have this kind of residual, the computation of the residual is here, and then you have a part in this subroutine where we need to implement the Jacobian. So again, if you want to contribute in an active way to the development of the SU2, we will, you can implement the Jacobian.
One or two spots where physical, but you know, I wouldn't call the whole solution into resolve, but you know, check out the mesh. Don't check out the solution. Don't assume that it's completely useless. I guess is what I'm saying. So, did anybody else have anything they wanted to add to the first one? No. Okay. Let's move on to the second one. So, Suman has posted. Can someone please help me with the command to run SU2 in parallel? Metis and MPI. I know about the parallel Python script, but can you please tell me the command how to run? So, and also a question about where the folders go. So, first, before I jump to the screen, I wanted to say we have a number of ways to code in parallel. First, we have a Python script that's going to automate everything for you. So, if you have Python installed, you know, with I think we only need the NumPy package for the parallel computation stuff. The optimization stuff needs SciPy, but for parallel, a Python distribution with NumPy. Go ahead and call that script, which I'll show in a second. That is going to call SU2 PRT conditioning code that decomposes using Metis. Call SU2 CFD to run the flow problem, and then it's going to call SU2 SOL for the solution execution. So the idea is, in parallel, we don't write the solution output files as we go. The idea is to save a little bit of effort during calculations and only write a restart at the end. Write solution files in any format you wish. And there's an add is a restart file. You can always call SU2 sol independently. Regenerate solutions. Generate them in a different format. Maybe you did it in tecplot format first, and then you want to go to paraview. You can do that. You can run it in serial or parallel. That's a little bit of an advantage. So why don't I jump over the screen and show you how we do this. So what I'm showing here is just our typical NACA 0012 Euler case. So in the folder, I've got the mesh NACA test cases, so you have access to this. And I also have a config file here for the NACA 0012 in Visid. And I just want to show you the two ways we typically call things in parallel. So first, we have the Python script that I mentioned. And so parallel computation, we use -f for the file, and then -n for number of cores. And you'll see when I hit this that the first thing it does is call SU2 PRT. So let me scroll back up and show you what's going on. So the first thing it does is called the mesh partitioning. Reads in the mesh, breaks it into 4 pieces here because I requested 4 partitions. It does that, it finishes the pre-processing, then it calls SU2 on the calculation, and like usual, it's going to print out a bunch of stuff at the beginning, info that you might need about your calculation, etc. It's going to print the residuals and whatnot. I'm just running it for 25 iterations, for example. And then finally, it's going to call the SU2 sol to take that restart file and merge it into solution files. So when you're finished, you're going to see that I have a surface flow, a flow.dat, history.py files that you're going to find in the repository left over. So if you want to do this manually, which clusters, because sometimes installing Python on clusters can be a little troublesome, you can always do this whole process manually. And so I'm assuming that I've already installed the code with MPI and Metis, like you said in your post. But if you want to do this by hand, there are a few steps. So first you're going to call the independently. So this is SU2 PRT. And I'm going to say -N4 for 4 partitions. And it's going to run and give you the same output it gave up above for the Python. So now you'll notice I have these 4 mesh partitions here, so the partitioning is complete. I can basically run the same command, so MPI run with, this is going to run the calculation. And while this is going, again to reiterate, we're not writing the tecplot or paraview solution files yet, we're only writing a restart. So at the end here you're going to see the restart file, and along with the history and a CSV that we are lightweight files that we're not concerned about. Thing is to copy, and this is an important one, that restart file to what we usually leave as solution flow.dat that we use for the solution. If you want, I usually leave it, but once you have this solution flow.dat, you can go ahead and make the same call you did before, but now to this is the solution export routine. And this is going to read in that restart, read in the mesh partitions, and write your files. So then at the end of the day, I have some tecplot to look at the solution.
I would like to add that apart from the metis that we are using now, we are working very actively in implementing a par metis partition inside the SU2. And even there is a version of SU2 that integrates the partition and the solver, everything together, so you see the different meshes generated by the partitioner. Is there anything else that we want to add in this?
Just note all the different flags that you can pass to
That's
Python.
right. Oh, good point. Including -help. Always remember you can check the options if you've forgotten. Just do Python, parallel computation -help. And another thing there, the Python scripts. So I mentioned that sometimes it's difficult to run on clusters or getting Python installed on clusters. The smart enough to know what type of environment you're using sometimes, and so if you're using something other than MPI run, that let us know. We can point you to where to change that if maybe you need to use MPI or you need to use srun for Slurm. If you have any problems like that, just let us know. We have a way to control that. So
it's a bit. And also, if you have any problem with Windows, we have an expert in Windows cluster that can solve those kind of questions.
Okay.
Yeah.
All right, let's keep moving then. So the next question is from Vino, and they're curious about how to carry out time-dependent compressible flow simulations. In particular, they want to know if they're time stepping, and they're interested in a planar shock problem where they want a time-dependent following of the shock. So, Santiago, what do you think?
Well, so yeah, and study simulations are very important, and I just wanted to say that next week we're having a workshop, and there's going to be a session on just using SU2 to run different types of unsteady simulations. So there's unsteady problems. Some of them are nature of the flow. There's either separation and you have a wake, which makes the problem unsteady, or the problem that he refers here, which is the shock tube problem, where the shock would move in time. But in SU2 you could also do unsteady problems if the mesh is moving, so you have grip movement, and that's an unsteady. time-dependent grid solver is, by default, is going to run a compressible solver. So you just leave that. Is it necessary to use? Well, it's necessary to specify an option for the unsteady simulation. You could specify, there's a few options. There's time stepping, dual time stepping, first order, and dual time stepping, second order. What people normally do is time stepping. And here what is you have an inner loop, well, dual time stepping because you have two loops. You have an inner loop where you can advance the solution like quickly, you can use in non-physical time, and then the outer loop advances the solution in physical time. So that's, I don't know, my preferred method. So I would go ahead and use dual time stepping. And if you're going to run for 10 seconds, so then what you have to do is you have to specify a time step, and you'll have to figure out what's good for your problem. And then you could either say run it for 10 seconds, there's an option for total time to run, or the total number of time steps to run. And you can pick either one to run for 10 seconds. Anything else?
Well, I think we have worked in the validation of the unsteady solver. In particular, there is a couple of articles in which we discuss a different turbulence model in order to run. It was the square cylinder.
David doing Rand's square cylinder case, which is actually in the test cases. So I'll mention that too. If folks want to play with some of the unsteady problems, flow over a square cylinder 2D that has nice shedding behavior. So that's a good one to see, a good one to start with. If you want a config file that has some of these options, you can just go grab that and modify it. There's some other options. There are pitching airfoils,
moving wall.
We have the spinning cylinder, and I think flow in a cavity. CFD 101, like the first thing you ever do, the laminar lid-driven cavity problem. So there are a lot of options in the test cases to check out.
We know that there is a community very interested, and we're improving the solver in order to provide a better method and more accurate solution.
Yeah, and in general, there are two options if you're doing dynamic simulations. It sounds like here you have a fixed mesh problem, but I'll at least mention we can transformations of the grid. We can also do dynamically deforming mesh. Find all those options under the dynamic mesh options section of the config file. So always remember you can check in the config template.cfg file that's in the root directory of the repository to see all these options. So
yeah, just a final comment. We are about the implementation in the compressible solver, but it requires some review the incompressible solver. So if you want to collaborate with us, it could be great if you can run unsteady simulation with grid movement and using the incompressible solver. Everything is working perfect.
Yeah, I'm not sure that we've had to test that yet, but if somebody's interested in working on that out there, please let us know. That'd be great.
Yeah.
Okay, let's keep moving on then. Aldo sends the next question. He says, or she says, they say, I have tried cases using triangular grids rather than quad grids. The triangular grids have been obtained by cutting triangles. Structured meshes are available on the NAS. The course's meshes are available. They've shared and so there's a difference here. I guess they're asking, there's a difference between the triangular mesh and the quad mesh. And Aldo is asking, why does it generate NaNs after a few nonlinear iterations? This is a common question. This is a good one. So did you guys want to say something about this one? Or did I jump? Oh, I'm sorry. Yep. These guys.
I would say when trying to modify your y plus values, just for SU squared for Rand's calculation, you want a y plus of 1 or less overall. And also with cutting those quadrilateral grids, you want to make your aspect ratio, you don't get very skewed grids. Both those can cause errors in at least your mesh file. And then once you've looked at the mesh, if you're still getting the NaNs, things to look at are if you're using like row second order with limiter, you might look at the limit. You might look at switching from second order to first, trying to get it converged in first order and then restarting and doing it in second order. Addition to that, you can reduce the CFL number That might help increase stability, and also check the multi-grid characteristics. And some of our test cases have developed the multi-grid over time looking with that mesh. Multi-grid parameters you import a new mesh might not always work the same way. So
Yeah, so setting the MG level is how we turn off the multi-grid, that might help. And also, this question, it's not clear to me whether or he or she is using the built-in divide elements.
I think that
flag.
he's not using that.
Yeah, so that's another thing to try, is to try to triangularize it using the built-in method.
Also, would you think it's likely that the reason why the grid makes a difference with the same config file is that cells have been cut?
I'm not a particular fan of dividing of the eyes.
Yeah, this is what I'm asking, right, is that in the boundary layer, it's really nice to have rectangular meshes. Flow is, the derivatives are mostly one-dimensional, right? The much more rapidly away from, and by having these nice quadrilateral high aspect ratio grid cells, you kind of keep the gradients nice. You have very nice estimates for the y gradients and nice estimates for the x gradients. Whereas when you divide into these triangles, now you have a cell that instead of looking like a square in x and y out of this, or in the normal and thing, you now have cut it. So now you have these derivatives that are sort of in both directions, which aren't quite as good in either direction. And since the gradients are very one-dimensional along the surface, that might be what's causing the actual NaNs, is less accurate gradient computation.
Yeah, that's a very good point. In fact, it's well known that you cannot use Green-Gauss gradient with this kind of divided grid.
But at the same time, I often find that the weighted least squares that has trouble when you do have triangles and prisms sometimes because the gradients are hard. So I think the short
Triangles and prisms, it's probably the fact that the aspect ratio is so great.
I meant squares work. I'm sorry. So yeah, to add one more thing. So I agree with what you're saying, Brennan. I wanted to add one more thing. In 3D as well, the same thing happens when you have tets near the surface. So you've got these diagonal edges that are now in the boundary layer that aren't normal to the wall. So typically, we'd like to have quads in 2D and prisms or hexes in 3D nearby.
The point is just first try first order. I think this is the starting point. No multi-grid, first order. If that is working, then we will move on. Unfortunately, we typically need a lot with the value of the limiter coefficient that is actually play, and I think you need to reduce one to a limit. So if I were you, I would try to reduce the value of the limit coefficient and
the
CFL number, no, and try again. And if you have a grid with the rectangle, much better than
it's also true that meshes are really important.
At the end of the day, the mesh is big. We have a bunch of knobs you can. Sometimes you have to go back and look at your mesh again. So, okay, let's. Any last comments on that one?
I guess another thing about meshes being so important, just with the pointwise people coming next week and talking about all these developments for the mesh, then it's a good way to, if you have a question, come to the seminar and ask it so you can learn more about meshing techniques, because meshes are
in fact important. This morning we received an email from Travis, so if you have any question related with grid generation using pointwise or solver or grid generator, just post your question in our CFD online forum. We replay also those kind of questions which we have.
Okay, so let's move on to the last question we have for today. This is by Suman. I'm working with SU2 and I'm looking to modify it and insert new solvers. So this is something that's very interesting for us. So the question is kind of some issues that are arising in the options HPP file. And in essence, the idea is kind of how do I add a new convective scheme versus, upwind versus center, et cetera, kind of clear up option structure. .hpp. So this one I will actually ask Annika and Brennan to chip in on.
Yes. The answer is you don't. The comment that's he's talking about in options, it's option structure.hpp. There are two, an enum upwind and an enum, not enum convective, enum centered. Upwind and centered. And if you you have an IDE or something and you go and search for a NUM convective, you'll see that it doesn't exist. So this comment is clearly fit a NUM convective that was useful. So you don't, for one, and this does kind of look really comment says you have a variable that doesn't exist. So if you see things like this that look fishy, please feel free to open up issues on the GitHub issue tracker, and we can examine them and see if they are issues. And if you also happen to know how to fix the bug, please feel free to submit a pull request. Note that we've now moved to you have to submit a pull request to the development branch. We only push to the master branch when we have new versions of SU2. So that way normal non-developers that are pulling from SU2 get sort of the most up-to-date stable copy.
Sure, and just one thing I'd like to add to that, because it seems like what you're interested in doing is adding a new convective. If you take a look through definition structure, you'll find the place where for each different mode of the solver, a class for which type of convective scheme will be used. And so if you look there, you can see what's being done already, and you can, if you write your own convective solver, well, that's the place where you would declare that that's the solver that you'll want to have used. The next place that you'll want to go is into the solver of whichever equation setting. So for instance, something like solver direct mean, if you want to look at the mean flow equation. And you can take a look at how each of the components of the numeric classes are called. And so I'm going to talk about this in detail in a workshop that we're doing next week, and I'll be showing some slides and hopefully try to make this a little bit clearer also. So we're going to talk quite a bit more about how to implement new equations. So look out for that.
Great. Any last things to add on this one, solvers and implementation? Yeah.
Well, I think the workshop that we have next week is going to be very useful. We are going to introduce a lot of interesting topics, in particular for the developer. I think the second day is going to be focused on the development of the code. We really want to encourage everybody to develop SU2 and also create pull requests, improve the documentation. There are a lot of things that we can do as an open source community, and we really are looking forward to those contributions.
Yeah, that's we have just a minute here, so that's a good segue into kind of wrapping up. I think that's a general theme. You've probably noticed a lot of activity lately aimed at growing the email list. We've got all sorts of exciting content coming. This is the last time we'll see you before the workshop, I guess. So, please check out the new developers email list. Join if you want to kind of get in on the discussion. There's still time and call in for the workshop next week. We'll be launching a new developer page with extra material, and we'll probably post the files from the workshop on that page afterwards, and videos. Somebody asked about videos. We will be recording the webinar and posting that. So really, we're very excited. This is a new initiative, and again, I just want to say, please post the forum. We're still working on the format, but if you have feedback on the format, if this is more useful, we really want to make it useful for the folks out there that are using and developing SU2. So I think with that, we'll sign off for today. Yeah.
Yeah. Thank you very much and see you next week.